Let's talk about cryptography for a little bit. So cryptography essentially means secret writing or hiding information. And it's been around since pretty much the invention of writing. One of the most famous cryptographic methods, called the Caesar cipher, was a method of encrypting what was written in a message simply by shifting all of the letters one letter down the alphabet. So for example, ABC would become BCD. Now if you do that to a sentence of English, you'll notice that the result is rather unintelligible and just looks like a jumble of letters. But if you know the key or the way to decrypt that message, you can very easily decrypt it back to a message that you can understand. So in today's world, cryptography is used in computers to keep conversations private. We're essentially trying to ensure pain. Privacy, authentication, integrity, and non-repudiation. Privacy is the secrecy of the message, essentially what we've been saying with cryptography, trying to hide the information contained in a message. Authentication means that you can trust the sender or that we know who the sender is. Integrity, the message is accurate to what I was intending to send, so it doesn't change from when it is sent to when it is received. And non-repudiation means that you can prove who sent it. There are several different types of cryptographic methods, or what we call algorithm classes. So symmetric algorithms use the same key for encrypting and decrypting information. We call it a shared secret key. So information that only the people on either side of the conversation are supposed to know. Symmetric algorithms are very fast. Computers can do them very quickly, so they're very efficient to send information back and forth encrypted with a symmetric key. However, there are a few issues with symmetric algorithms. For example, how do you share that initial key? Especially when we talk about conversations across the internet, if we want to transmit the key to a particular individual, how do we get that key to them without sharing it with everyone else who can observe that conversation? It's a very difficult thing. Non-repudiation is the other issue. Now remember, non-repudiation is that we know who sent the information. If we have multiple people in a conversation where a symmetric key is in use, let's say we have 5 people, it becomes very difficult to prove who sent the message, since any one of the 5 people could have sent the message with that particular secret key. An asymmetric algorithm solves much of these problems. However, it's more difficult for computers to use, both generating the keys and encrypting the information with the keys. In an asymmetric algorithm, we use 2 different keys for encryption and decryption. We call this a public key and private key pair. The private key is always held by one person, and that person alone. Anything encrypted with a private key can be decrypted with the public key. Likewise, anything that's encrypted with a public key can be decrypted with the private key. Now this solves our key sharing issue because the public key is public to everyone. It also solves our non-repudiation issue because the private key is only held by one person. So anything that is decryptable by the public key must have been encrypted by that private key, and there's only one person who could have encrypted it with that. So let's look a little bit more in depth at asymmetric keys. So there are 3 different ways to use asymmetric keys for an encrypted conversation. The open message format is one where we essentially want to prove that we sent it, but we don't care who reads it. And so we use our private key in order to encrypt that message. Anybody then with the public key, which is everyone else, would be able to decrypt it and essentially understand or know that we were the ones who sent it. We often call this digitally signing for authentication and non-repudiation. Another way we might use an asymmetric encryption algorithm is the secure message format. Perhaps we want to make sure that only one person can read our message. So we'll encrypt our message with their public key so that only they can read it. Now, of course, putting these 2 together would be the best way to do it. We call this mutual authentication, and we essentially encrypt our message with our own private key as well as the public key of the intended recipient. That way, only they can receive it, and it proves that it comes from us. They would then decrypt it with their private key and our public key in order to look at the original message. Now, of course, the downside, as we've already said, to asymmetric encryption is that it is computationally expensive, both to create the key up front and then to encrypt and decrypt that information. However, asymmetric encryption does present a good opportunity for us to share a secret key for symmetric encryption. For example, we could put the secret key for symmetric encryption into a mutual authentication conversation and then use the symmetric key for the rest of the conversation. That way, the symmetric key was shared secretly, and only the two people in the conversation are using that key. So a combination of asymmetric and symmetric algorithms is very useful for sending information securely and ensuring privacy, authentication, integrity, non-repudiation. Now, the last algorithm class is actually a hashing algorithm. Hashing algorithms are one way, meaning that information is lost when we use it to encode information. Or in other words, the encoded message can't be decoded. We use hashing algorithms to ensure integrity. In other words, to reduce a message into a smaller value that's representative of the message to make sure that the message reaches the endpoint without having been modified. We also use hashing algorithms to store passwords on computers. Now, passwords don't encrypt or decrypt particular systems, but they are a good way for ensuring confidentiality. Let's talk about passwords for just a moment. Passwords are the least expensive and the easiest way to increase confidentiality on a particular computer. Now, most computer systems today have a password system built in already, which is why they're incredibly inexpensive. It simply takes the time to create a password on a particular system. Passwords are useful for restricting access to a particular computer, increasing confidentiality, but that also assists in protecting integrity. Now, it's important to note that the activity of password cracking and password recovery are essentially the same. We're going to use the same tools to try and crack a password as we would to try and recover a password that's lost. However, the difference is when we're doing password recovery, we have permission to recover that password. While password cracking, we do not have permission to crack that password. A strong password is a password that is difficult to crack or to break, to guess. The longer a password is, the stronger a password will be. However, strong passwords can be hard to remember or recover. So there needs to be a balance between the complexity of the password and how well you can remember what that password is. Of course, if you need a strong password and you're afraid that you will forget it, you can always use a password storage tool like LastPass or 2Remember. Putting passwords in an unprotected Excel spreadsheet on your desktop is not a very good idea. The strength of a password should always be proportional to the importance of the data that it's protecting. Default passwords, common passwords, and associative passwords are often easy to guess and therefore not usually a good idea to use if you're trying to secure a system. Default passwords include words like admin, password, 1234. Common passwords such as birthdays, pets' names, etc. are often used, and associative passwords are passwords that relate to a particular system or person and might be easy to guess based on the association with that particular system. When choosing a strong password, try and focus on the length more than the complexity or the character set of that particular password. 8 to 12 characters is a good length for most systems. Longer passwords will be more secure. As far as complexity goes, try and make the password alphanumeric using both letters and numbers. Symbols can also be useful, but can also add confusion and make it difficult to remember what the password is.